about everybody did angular integrations which weren't really necessary. In other words, you found that the divergence of some vector field, I forget what r squared r hat, I think it was like, what was it, 4r to the fourth or something like that. Just r to the fourth, do you remember off the top of my head? It's not 4r. What is it, 4r to the fourth? Or just r to the fourth? What?
Well, just the divergence of it is just 4r.
It's just,
Yeah. But then when you plug it in, yeah.
Oh yeah, 4r. Okay, yeah, 4r, right? Okay.
And then it becomes
So,
4r.
right, yeah. So then it becomes 4 pi r to the fourth. Integrate over the sphere. So the idea is we have this sphere of radius r, and you want to find the integral of div v d tau. And what just about everybody did was say, okay, well that's going to be 4r times r squared sine theta dr d theta d phi, and then you did the integral from r equals 0 to r, and theta equals 0 to pi, and phi equals 0 to 2 pi. But sure, that'll work, fine. Certainly won't take off for that. But when you have a situation like that, your integrand only depends on r, which means that you can pre-do the angular integrations. In other words, if I integrate sine theta d theta d phi over all directions, what do I get?
0.
No, not 0.
2.
No.
Wait, sine theta d theta?
If I integrate sine theta d theta d phi over the sphere, that's 4 pi, right? Because this is, in fact, the element of solid angle, d omega sine theta d theta d phi. That just plain integrates to 4 pi. So you can just right away write that it's 4 pi for the angular integration. But even better than that is to just realize this thing only depends on r. You're doing a volume integral. So in other words, what you should be doing is integrating over spherical shells. In other words, for your volume element, you should use a shell whose thickness is dr and whose radius is r, and so therefore its volume is equal to, I have a spherical shell, radius r, thickness dr, it has volume of 4 pi r squared dr. That's right, 4 pi r squared dr, right? Because it'll be area times thickness, and the limit is the thickness becomes infinitesimal. Area times thickness is the volume of that shell. So just use d tau as 4 pi r squared dr, and get into the habit of doing that. If you're in spherical coordinates and you got something that only depends on r, and you need to do a volume integral, use d tau equals 4 pi r squared dr as your volume element. Think of integrating spherical shells. So then you're just doing 4r times 4 pi r squared dr from 0 to r, and that immediately gives you 4 pi r to the fourth. It's easier to do that than to bother with doing the angular integrations, because whenever there's no dependence on angle in the integrand, the angular integrations, if you're integrating over the whole sphere, are guaranteed to give you 4 pi, because it's always going to work out that way. So that's the 4 pi right there. That's from doing the angular integration, or pre-doing the angular integration, so to speak. So simplify that volume element if you have the opportunity to do so, because of course the more integrals you do, the more chances you have to screw up, and so it's better to avoid that. Okay, I think that was my major comment from the homework. I certainly didn't take anything off for doing the angular integrals, and in fact, in the solutions manual, the author always does the angular integrals, and I think, but in any case. So I won't hold that against you. All right, so onwards and upwards with our discussion of potential. Example 2.6 says, find the potential inside and outside a spherical shell of radius r which carries a uniform surface charge. I'll just reword that as find V inside and outside a uniformly charged spherical shell. Okay, so here's our uniformly charged spherical shell, and let's say that it has some radius r. Okay, well, that's my almost spherical shell there. Outside said spherical shell, what's the electric field? Let's say that the total charge on it is Q. What's the field? What's the electric field outside said spherical shell? Say if I'm at a point of distance r away from it. Well, is that spherically symmetric? Yes, it is. What do we know about a spherically symmetric charge distribution? It acts just as though it were a point charge at its center, right? You can derive that from Gauss's law. You can do it every time you see this. You can say, I can draw a spherical Gaussian surface around it, and by symmetry, the electric field is everywhere outwards, and so therefore the flux is the electric field times the area, so 4 pi r squared E is equal to Q enclosed over epsilon naught, and therefore E is Q over 4 pi epsilon r squared. Get it from Gauss's law, certainly, and I hope you can kind of instantly do that, but also you should just knee-jerk reaction, every time you see a spherically symmetric charge distribution, you say, aha, it acts just like, as long as you're outside of it, it acts just like a point charge located at its center, so therefore E is Q over 4 pi epsilon naught r squared, r hat, when you're outside the charge distribution, in other words, when r is greater than big R. Excuse me. What about inside? Come on, Steph. 0, yes. Inside it's 0. In other words, remember the general rule is when you're dealing with a spherically symmetric charge distribution, only the charge interior to your radius matters. So if you're inside this sphere, then you don't get any electric field because the electric fields of all the pieces cancel one another. If you did the Gauss's law thing, you draw a Gaussian surface and say, well, if there was electric field, it would be everywhere perpendicular to that surface, and so the flux would be E times its area equals the charge enclosed, but wait a minute, there's no charge enclosed, therefore the electric field must be 0 by the symmetry of the situation, right? Remember, it's not true that just because the flux is 0, the electric field is 0, but in this symmetric situation, the fact that if there was an E, it would be the same everywhere, and the fact that the flux is 0, no, not the same everywhere, but everywhere perpendicular to the surface, and the fact that the flux is 0 implies that the electric field must be 0, because if it wasn't 0, there would be a flux through the surface. So E is equal to 0 for R less than R. And so in other words, the potential is the same it would be for a point charge outside the sphere, and then we have to figure out what happens inside the sphere. Now all of a sudden I can't remember. Did we go over yesterday where we want to choose the reference to be at infinity? Yeah, okay, not yesterday, but on Tuesday. I'd forgotten. So we did that. We said we want R to be, yeah, we did. I remember now. Okay, what? Okay, so if we're looking for V of R, notice I didn't put a vector on that because it's spherically symmetric, so it's only going to depend on distance from the origin. So V of R will be the same as for a point charge Q at the origin when R is greater than big R, because, V of R is going to be equal to the line integral of the electric field minus the line integral of the electric field. And if you're in a region outside the charge, the electric field you're integrating would be the same thing as you would integrate for a point charge at the origin out there, because the electric field looks the same. So that if the field is the same as for a point charge, so too will be the potential. So what is the potential for a point charge at the origin? This is one you should memorize.
At the origin.
at the origin, for a point charge at the origin, I'm not saying what's the potential at the origin, it's infinity. I'm saying for a point charge at the origin, comma, what is the potential as a function of r? Q over, say that again?
4 pi epsilon 0 r.
Where's the Q come in? And
It's just that same formula except r squared.
yeah, exactly, right. Same formula, but r squared gets replaced by r. Yes, exactly. So Q over 4 pi epsilon naught r. So remember that electric field, Coulomb's law is Q over 4 pi epsilon naught r squared for a point charge. For the potential, it's just Q over 4 pi epsilon naught r. That's what we derived when, now I'm remembering, on Tuesday, we said, oh, where should we choose the reference point? And the answer was at infinity, because in general you get Q over 4 pi epsilon naught times the quantity 1 over r minus 1 over r for the reference point. So you let the reference point be at infinity so that 1 over r for the reference point is equal to 0. So then you just get 1 over r times Q over 4 pi epsilon naught. So this is what you get for r being greater than r. Okay, any questions about that? Is that reasonably obvious to you that that should be the case? Or if it's not obvious, let me know. Happiness and joy? Or something vaguely resembling it? Okay, what about inside the sphere? Without looking at the notes, what about inside this sphere? What should the potential be? You might think at first 0. What's the electric field inside the sphere? 0, but does that mean that the potential is 0? No. It has to be constant, right. It has to be constant inside the sphere, because if E is 0, then if I integrate E to a line integral between any 2 points, I get 0, so the change in the potential is 0 between any 2 points inside the sphere, because integrating the electric field along any path where the electric field is everywhere 0 is going to give 0 potential difference. Remember, the line integral of E between any 2 points minus the line integral of E between any 2 points is the change in the potential between those 2 points. So we know that V is a constant inside the sphere, and what does that constant have to be? Well, what is it right at the surface? What's the potential right at the surface? Oh. Speak up.
Q over 4 pi epsilon naught big R?
Yes, Q over 4 pi epsilon naught big R, because here's the formula outside the sphere. So as I approach the surface of the sphere, when I get right to the surface, the potential is Q over 4 pi epsilon naught big R. Just using my formula. But since V is a constant inside the sphere, that means and everywhere interior to the surface as well. So for any r less than or equal to big R, the potential is a constant Q over 4 pi epsilon naught big R. So it's important to keep in mind that just because the electric field is 0 does not in any way imply that the potential is 0. It implies that the potential is constant over any region where the electric field is 0. A very different thing than implying that the potential is 0 there. Now this is with our reference point being infinity. So certainly we could make the reference point the origin if we wanted to. We could force the potential to be 0 inside. We don't have to do it this way, but by convention we pick the reference point to be infinity. So if we set the potential to be 0 at infinity, then the potential in this inside the sphere is Q over 4 pi epsilon naught big R. What's going to be true no matter where we pick the reference point is that the potential difference between the inside of the sphere and infinity is Q over 4 pi epsilon naught big R. Okay? Any questions? let's then talk about the energy of a distribution of point charges. We're going to start with point charges and then generalize to a continuous charge distribution, and we'll see that there's an important distinction to be made in this case between point charges and continuous charge distribution. So what we're asking here basically is ultimately going to be how much work would we have to do to assemble that distribution of point charges, where by assemble I mean start them off very far away from each other, effectively infinitely far away from each other, and then drag them together, make them congregate. If it's a plus and a minus charge, well, they want to congregate anyway, and so that'll have negative energy associated with it. They like each other, they'll have negative potential energy. If it's a pair of positive charges, on the other hand, they don't like each other, you would have to do positive work on them in order to bring them together. So for point charges, the configuration energy can be positive or negative. It could go either way, depending on if you got like charges, unlike charges. If you got 13 plus charges and 7 minus charges, well, who knows? It's going to depend on the details of what the energy of the configuration is. So we'll start with an assembly of cute little point charges plus one ugly little charge there. But we will assume that it's small enough to be treated as point length, even though it's not quite. All right. Yeah. So here's an assembly of point charges, and we'll give them a label QI. So, you know, that's QI, but any of them could be QI. You know, they're Q1, Q2, Q3, Q4, etc. A bunch of point charges labeled with some index. And now we've got 2 points in space, A and B, and big Q is going to go in between points A and B, and we want to know how much work an external agent would have to do to pull that off. We're going to move Q between A and B such that its kinetic energy doesn't change in so doing. Okay? So, this is what we ask ourselves. Question: how much work must one do to move Q from A to B with no change in speed? We don't want to waste any work on creating kinetic energy. We just want to go there with no change in speed. Okay? Answer. We know that the electrostatic force holds Republican. It is in fact a conservative force. Or in other words, that you can associate energy conservation with it. So in this case, the work done by the external agent, so we're not talking about the work done by the electrostatic force itself, we're talking about the work done by us as we drag the charge around with no change in its kinetic energy, will be equal to the change in the kinetic energy plus the change in the potential energy. In other words, the total change in the energy. If I do work on some system, that work changes its energy. It can go into changing the system's kinetic energy and or into changing the system's potential energy. So the work done by the external agent, Wx, is the change in the kinetic energy plus the change in the potential energy. But we're going to do this so that we don't change the kinetic energy. We wanted to do this at constant speed. So in other words, the work that the external agent's going to do is going to only change the potential energy of the system. And as we saw before, the change in the energy of the system will be the charge multiplied by the change in the potential between those 2 points. So the potential energy I'm giving to the system by doing this work on Q will be equal to, another way to put it, it's minus the work done on Q, right? The change in the potential energy is minus the work that you do on Q. So it'll be minus QE dot dl integrated between points A and B, in other words. So what we're saying then is that what we need to do is to balance the electric force that's exerted on Q in moving it between those 2 points. And actually it's a little more subtle than that, because even if I'm not changing its speed, if I move it on this path, is that charge accelerating? It is, right? Because acceleration is any change in velocity, and even if it's moving at constant speed, it doesn't have a constant velocity here. It's moving on a curved path. So the direction of the velocity is changing. However, what this will mean basically is that my force has to exactly balance the component of the electric force on it along the path, plus I have to exert a force perpendicular to the path to give it the radius of curvature that it has at any given moment. In other words, if I have this piece of chalk right here, right? Is there any force on this piece of chalk? Yep. What direction does that force point? Oh, I'm getting sick now. Anyway, what direction is the force point? Towards me, right? I have to have a centripetal force on it, right? I have to have a force perpendicular to the direction that it's moving. So I have to produce a force on this which is minus the electric force on it at each point, and then also whatever force perpendicular to the path is needed to give the path its curvature. But does a force perpendicular to the motion do any work? Am I doing any work on this right now, pulling in on this piece of chalk? I'm not doing any work. Why not? Ah, blank stares. Okay, so if I've got something moving in uniform circular motion, right? I got something moving in uniform circular motion. Is its kinetic energy changing? Nope, right? Uniform circular motion means around a circle at what? Constant speed, right? So, no change in its kinetic energy, but there is a force being applied to it. And I thought if I apply a force through a distance, I get work. So how can that be? I thought work was supposed to be changing kinetic energy, but this thing is not changing its kinetic energy, and yet there is a force on it. Huh? How can that be? Because what? Yeah. Remember that work is the line integral of force dot dl, right? If the force is perpendicular to dl, then you're not doing any work. So what I'm saying here is that, okay, there is, basically what I'm saying is that any work, any force that is exerted on this thing just to give it the curvature of its path there isn't going to be doing any work on it. Okay, so if we balance out the component of the electric field along the path, then there'll be no net force parallel to the path, and so it'll just be sliding along at constant speed instantaneously. But you'll also need a component of force perpendicular to the path if the path is curved in order to have it instantaneously moving on an arc of a circle at any given moment along the path. But any force you apply, any force component perpendicular to the motion isn't doing any work on it. So the total force is there's no net force along the path at any given moment, and there's a force perpendicular to the path, which is not doing any work on it, providing the curvature. So you balance the electric force on it with the force you're applying along the direction it's moving instantaneously, and then you also apply a force perpendicular to it to give it the curvature. You make it curve along its path. And in the end, what that means then is that the work, the work that you're doing externally has to be equal to minus the electric force on it, integrated between A and B, the line interval there. The work you're doing is equal to minus the change in its potential energy. I mean, it's equal to the change in its potential energy, which would be minus the line integral of QE dot dl. QE isn't the only force you're applying to it, but the net work you're doing is just changing the potential energy, which would be minus the integral of the force dot dl, the electric force dot dl, so minus QE dot dl. Seeing lots of blank stares here. So, but in any case, even without worrying about all this parallel and perpendicular component stuff, well, you buy this, that any work you do goes into changing its energy, so any work you do is going to change its potential energy and its kinetic energy. By assumption, we're not changing its kinetic energy. We're deciding we're going to move this thing at constant speed, right? Here's this piece of chalk. I'm going to move it at constant speed, so I'm not, so if any work I'm doing is only changing its kinetic energy here. What? I'm sorry, it's only changing its, thank you, here. It's only changing its potential energy here, right? Yeah, nobody caught that, right? Right? Don't know how long to keep banging on this point here, but all right. If I drop this, what's going to happen?
It's gonna fly
It's going to fall. And what's it going to do as it falls? It's going to speed up. So, if I consider the system to be the Earth and this piece of chalk, and me to be the external agent, is there any work being done by an external agent as that thing falls? No, right? Because though no external agent's applying a force, the force is all internal to the system of the Earth and the piece of chalk. Okay? So, as this thing fell, its kinetic energy increased. What happened to its potential energy? It decreased. And how did the change in the kinetic energy compare to the change in the potential energy? Why, they were the same, right? It conserved energy, right? When it fell, okay? What if I throw it upward, right? Whee! Okay? As it was rising, the kinetic energy and the potential energy, and how did their changes compare? They were the same. All right, now suppose I take this piece of chalk and I lift it at constant speed, right? Then, how is its kinetic energy changing? It wasn't. How is its potential energy changing? It was increasing. Where did that increase in its potential energy come from? The work I did on it. Yes, the work I did on it. All right.
every day.
Sure. It's from the work I did on it. Okay. What's the force? What are the forces on this thing as I'm lifting it at constant speed? There's me, right? Which direction am I exerting a force? Up. And then what else is there acting on it?
Gravity.
Gravity, and it is... No.
Sorry.
Now. Smart aleck. Okay. Gravity is down, right? So the force I exert and the force of gravity are equal and opposite as I raise this thing at constant speed, right? So therefore, there was no net force, and so therefore is moving with constant kinetic energy. There was no work being done. So the work I was doing was increasing its potential energy. All right? Now suppose it moves on a path like this at constant speed. Is the force I'm exerting on it, in that case, only downwards? No, right? It better not be, because if the force I was exerting was only downwards, then gravity would balance that force, and how could it be moving on a curved path? right? It couldn't be. It can move on a straight path with no net force on it, but it can't move on a curved path with no net force on it. So, what is happening when I move this thing on a curved path at constant speed? It's still true that the work I'm doing is increasing its potential energy, and that's all that my work is doing. It's increasing its potential energy because its kinetic energy is staying constant. So what's happening is that in addition to balancing gravity, I also have to exert an additional force perpendicular to the path at every moment that is giving the path its radius of curvature, its instantaneous radius of curvature. So that, overall, the net work is still just the work I'm doing against gravity, because the forces perpendicular to the path aren't doing any work. And so that's the deal here, too. The forces that are just giving the path its curvature, perpendicular to it, are not doing any work. So in calculating the work gravity does when I move it on this complicated weirdo path at constant speed, it's still true that I can get the work just by integrating the force that I'm putting against gravity on it. In other words, the mg force is all I need to consider when I'm calculating the work that I'm doing on this piece of chalk. Is there something resembling happiness with that explanation? Yasser's just staring at me funny. Yes?
I'm sorry to continue the conversation, but you say no change in speed there, so is it already moving?
Yeah, yeah. So, right, yeah, it's certainly true, I had to give it kinetic energy here, right?
Okay.
So if you like, I started it just before point A and got it up to speed and kept it going up to speed right up to point B, and then I stopped it right after point B, okay, if you like, yeah. Or you can say, let's move it at negligible velocity the whole time, something like, so we don't have to worry about that little jerk. But yeah, that's right, that's a good point. So it's already, strictly speaking, got to be moving. Or if you like to, if I move it at constant, if I start and stop, right, there's still no change in kinetic energy. So it's still true even in that case. There's no change in kinetic energy if I start and stop. The net work I did was only equal to the change in the potential energy. So this still gives the right result. Even if, really what's important is that it has to have the same speed at the beginning and the end. Even if I make it speed up and slow down, the net work I do is just given by this in either case. Because along the way, I would be doing some positive work on it for a while and then some negative work on it that balanced that out. So that still, overall, the work I did only changed its potential energy. Yeah, so that's actually not a dumb question. That's a very good question. It's a good point to make. Yep. Okay, any other questions? Or just comments? Go ahead. Throw chalk. Oh, that seems like a good idea now. Just a small one. Oh. What? Oh. Nothing. Yes. Okay. All right. So, having pulled those teeth,
It's rather painful.
yes. So this is going to just be Q times the potential difference between those 2 points. Right? Minus the line integral of v dot dl is the change in the potential. So Q times the change in the potential is the work I do, or in other words, the change in the potential energy is the work I do, because charge times potential is potential energy. Okay? Well, it's often convenient to think of Q coming in from infinity. Or in other words, in a sense then what we're saying is, if I bring in Q from very far away, how much work does it take to do that? And so effectively you can approximate you're bringing it in from infinity. So approximately, well, again, it's approximately right if we're going really far away, is what I'm trying to say there. Then, in that case, we would get that the work done by our external agent to bring Q in will be V of R minus, if we bring it to some final position R in whatever our coordinate system is. So, you know, we could draw some axes here, and then remember that it's always, we're talking about position vectors here, so that was position vectors A and B. Well, now if we just select the final position vector of Q be R, and the initial position vector is off at infinity, then the work done will just be the charge times the potential at R minus the potential at infinity, but the potential at infinity we've set to be equal to 0, and so therefore you just get Q times V of R. Notice that does have a vector on it because with our complicated charge distribution, there's no implication that it only depends on distance from the origin. Potential some complicated function of the position of the charge. So that's how much work we have to do to bring in a charge from very far away to our distribution of charges. Why are they laughing at me? Do you know?
They're probably not laughing at you if both of them are laughing.
Yeah, they probably just have a
It's
little.
so embarrassing. Tell us now.
Yeah, that's okay.
For who?
Tell us now.
Yeah, who's going to be embarrassed?
It's not really embarrassing.
Oh,
Share it.
as long as I'm not going to be embarrassed, you know, then I'm okay. to have
Me too.
this.
Elsa wrote, Hermione Granger eats food. On the note.
Remind what?
Hermione Granger eats poop. Harry Potter.
Oh, well then. Is that actually from Harry Potter? Is
No,
that actually
clearly
not.
Because I know who Hermione is and all that, but I was
If she
just
does
wondering if
not.
that was from any of the books.
Basics.
Okay. All right. The word of the day is Hermione. I had a choice. I went with Hermione.
That's right, I was going to say. It's the beginning or end.
Yes. Okay.
She's trying.
Well,
It was so dumb.
all righty then. So,
On that note,
that
that worked.
yes, I don't know how to proceed.
And we're done.
And we're done. That's right. So, that's how much energy it takes to bring one charge in from infinity. So what if we want to know how much energy it would take to assemble this entire distribution in the first place? Well, what we can do is we can say, okay, let's bring in the first charge, and then we'll bring in the second charge to its location, and then we'll bring in the third charge to wherever we want it to end up, and then we'll bring up the fourth charge. And so we'll just add together the work needed to bring each charge in one at a time. And when we do that, we'll discover we get this sum that's completely symmetric in all of the charges, so that it wouldn't have mattered which one we brought in first and which one we brought in second, so that we can sensibly say there is an energy of the charge distribution that's independent of how we brought them together.
Say that one more time. I'm just kidding.
What, that.
Thank you.
How much work to assemble the whole distribution? Okay. So, we'll just draw a picture here that has 3 charges in it, even though we're going to bring in 4 charges and then generalize from that. But if I had 4 charges in my picture, there'd be way too many cross lines. Whereas with 3, you just make a nice little triangle. So, here's our 3 charges. Draw the triangle then, identify the vertices. Here's our 3 charges here. And so charge 1 ends up at position vector 1, charge 2 ends up at position vector 2, and charge 3 ends up at position vector 27. So now we have Q1 coming along, not Q1 is coming along that path, let's say, and ending up at R1, and Q2 comes in along here and ends up at R2, and Q3 comes in along there and ends up at R3. And so here's our beloved script R12, the vector pointing from R1 to R2. And here is beloved R23, and here is beloved R13. So we can put little arrows on there, or we just take the arrow symbols off and just make them be distances. Doesn't really matter. So if we bring in Q1 first, and all the other charges are way, way far away, and always way, way far away, how much work does it take to bring in Q1? If it's always very far from the other charges, it's Q times V of R1, but if all the other charges are not there yet, what's V of R1 effectively? It's 0. If all the charges are infinitely far away to start, and then I bring in Q1, basically what I'm saying is, it doesn't take any work to bring in Q1 because the other charges are so far away that there's virtually no electric force due to the other charges on Q1. So when I integrate the electric field, I'm integrating 0. Or alternatively, if all the charges are infinitely far away, the potential is 0. Right? Not quite, you know, if they're at any finite distance, but if they're infinitely far away, it doesn't take any work to bring in Q1 because there's no field of the other charges to worry about. So Q1 comes in for free, W equal W1, we could say, call it the work done to bring in Q1 is equal to 0, since all other charges are infinitely far away. Infinite, right? That's the special symbol for infinite. For Q2, we have to do work against the field of Q1. If they're both positive charges, they're repelling each other. So we got to force them to come together. So we're going to have to do positive work. We're going to have to drag the charge in, exerting a force in the same direction, essentially, that the charge is moving. And so that's going to cost us.
Are we assuming that all these charges are the same?
That what?
Are we assuming that all the charges are the same?
No, they can be different. And if they're opposite, if they're, you know, Q1 is positive and say Q2 is negative, that'll do negative work because they'll be attracting each other. So I'm going to have to hold them back. And so I'll be pulling opposite to the direction that the charge is being moved. And so I'll be doing negative work in that case. Okay? So we get either a positive or a negative result for this. So in other words, we're going to get W2 is going to be Q2 times P of R2, going back to our handy formula back there. And V of R2 is just going to be equal to Q1, well, I'll just write it out, okay? It's going to be 1 over 4 pi epsilon naught, and then we'll have Q2 times Q1 over script R12. In other words, V of R2 will be the potential due to charge 1 at the location of charge 2. Right? V of R2, R2 is only seeing at this point the electric field of charge 1, so the potential at R2, when we bring in Q2, will be the potential due to a point charge Q1 sitting at R1, so that'll be equal to Q1 over 4 pi epsilon naught times script R12, the distance between them. It's the potential of a point charge is Q over 4 pi epsilon naught times the distance from the charge. Okay, so this is what we've got so far. And then after break, we'll bring in charges 3 and then charge 4, and then we'll say, hey, there's a pattern here, so here's the final result.
Real quick, does anybody like go
you.
What?
Because my roomie Sam brought them home from her work last night, but I don't like raisins. So
You don't like raisins?
I have 3 oatmeal raisins and he's going to and I'll just have them right here.
And you guys just wow. Yeah, okay, we'll go with that.
All right.
Also a designated hitter, right, so I like that, yeah. Okay, yeah.
See, I don't play.
And then you put like a ball cap on it.
We should all wear it to class one day and be like the coolest people ever.
That's right.
I like pop out a corner and then
We're all
like
going to
kind
class,
of
and then someone's like,
The thing is,
really?
not much nothing. Pop out from somewhere else.
It's we have games today.
Yeah,
We all have to wear a
No,
shirt.
big observing session coming up later.
I really would.
Every time we get in the
I
shop,
really
club meetings. Oh, for Perkins, you have to wear it, it's like game day.
We have to,
Ooh, I'm so funny.
So, if you so say yourself, say so, blah, blah, blah. Okay, for Q3, we have to do work against the fields of Q1 and Q2. So, W3 will be Q3 times V of R3, but by the time Q3 has come in, then V of R3 consists of a contribution from Q1 and a contribution from Q2. So in other words, we're going to have 1 over 4 pi epsilon naught times Q3, parentheses, sum of Q1 over script R13 plus Q2 over script R23. So for when we bring in Q3, we've got 2 charges that are contributing to our potential energy. And now, not pictured, we bring in Q4 again because I didn't want to draw a little cross, things between all of them. Could, but I didn't want to. So for Q4, bringing in Q4 is going to take W4 equals 1 over 4 pi epsilon naught times Q4 times, well, okay, now we're going to have Q1 over script R14, distance from charge 1 to charge 4, plus Q2, script R24, plus Q3, script R34. And so you can see, what you do if you brought in Q5, then you have 4 more terms, which are R15s, R25s, et cetera, So our total work to assemble the system well, that's going to be W1 plus W2 plus W3 plus W4. And so our total W, the sum of all those, will be 1 over 4 pi epsilon naught. And then we'll have Q1, Q2 over R12 plus Q1, Q3 over R13 plus Q1, Q4 over R14 plus Q2, Q3 over R23 plus Q2, Q4 over R24.
Please stop.
Wait,
Plus.
what's Q13?
Huh?
No, what's Q4?
Oh, that's
I was like,
there you go.
U13. I could
See
be
that?
wrong.
Because they're pounding.
All right, let's amend
Got
appropriately.
it.
Yes, okay. Plus, one more, Q3, Q4 over R134. So, if we had charges 1,763,000 in there and 1,764,000, we got Q1,763,000, Q1,764 over 1,763,000, 1,764, and so forth, which would get a little tedious. But in any case, there's a pattern here. In other words, what we've done here is we've got every possible combination of pairs of charges divided by the distance between them. And so that means that if we have a bajillion charges, then we would sum 1 over 4 pi epsilon naught times the sum from I equals 1 to a bajillion, and I won't put the upper limit on there, it'll just be understood that, you know, the upper limit is whatever it is, and the sum for j greater than I up to a bajillion of qi qj over rij. The reason we say j greater than I is because otherwise we would include both, for example, q1, q3 over r13 and q3, q1 over r31, but those aren't different from one another, right? I mean, you know, q1, q3 is equal to q3, q1, and r script r13 is equal to script r31, not the vectors, but just the distances between them. It doesn't matter which way you go. So in other words, the j greater than I there is to avoid double counting. We only want each pair of charges to appear in this sum one time, so we can do that by assuring that the index j is always bigger than the index I, just like I put it in the summation here. The second index was always bigger than the first index. So we can't just sum on I and j. We have to explicitly say that j has to be greater than I when you do the summation. Or we can just say, the hell with it. Let's just go ahead and double count and just divide by 2 in the end. So the other way to do it would be, we could just double count and divide by 2. So we could also say that the work is half of 1 over 4 pi epsilon naught, and yes, that's 1 over 8 pi epsilon naught, sum over I, j not I. J not equal to I is the other sum of qi qj over rij. Then you'll double count, but you'll divide by 2 and it'll take care of it. Meanwhile, I don't want to let I still have to say I not j, j not I, because otherwise you'd have things like q2 over r22, but r22 is equal to 0, yes. And 1 over r22 is infinity, and it would blow up. And as we'll see, that's kind of the key to why continuous distributions and point distributions are different from one another. In other words, notice that we haven't said anything about how much energy it would take to create one of these charges. If you think of one of these charges as being composed of little bits of charge that you brought together at a single point, that would take an infinite amount of work. So the charges themselves, in a sense, require infinite amount of work to assemble, and we're just throwing that away. We're taking the charge as being pre-made for us, already given to us, and we're only worried about the interaction energies between the charges, not the mysterious energy it would have taken to make the charge in the first place, if there even is a sensible thing to talk about there. Okay, so any questions? All right, so here, the fact that every pair appears in this symmetrically, either way you do it, you know, every pair is in exactly the same way. In other words, every pair appears in the sum, and then divided by their separation. Means that in the end it wouldn't have mattered which order we assembled these things. Because every pair shows up in exactly the same way in the sum, then the order of assembly is immaterial. You could have brought in Q4 first, and then Q2, and then Q1, and then Q3. You would have gotten exactly the same result. So, in other words, we can sensibly talk about the energy of this configuration and not have to worry about its history. There's no dependence on how the assembly was created, the order that we brought them in, the path that they took. The only thing that matters in the end is their final configuration, where each charge is, how far they are from all of the other charges. Okay? So, happily, we can speak of the energy, and also, we can factor we can factor Qi out of the sum on J. So we could say that the of the sum on I times the sum on of epsilon A. And the point of that is that what's in the brackets here, this sum, is the potential at the location of charge I due to all the other charges in the system. I've just added up the potential due to all the other charges at the location of charge I, because the strict Rij's are the distances between each of the other charges and our particular charge I, one at a time, that we're looking at. So in other words, we can say that the work is equal to 1/2 times the sum over I of Q sub I times the potential at the location of charge Q sub I, charge I. So 1/2 times the sum of each charge times the potential at its position is the total energy of the system. It's another way of saying this. And those two are back to giggling again.
This one is a Nick joke.
It's a
Whenever
what?
I clear my throat, I go, and Nick always makes fun of it.
Wow.
Do it again.
I can't, Nick can do it pretty well. Like right now, I can't even do it because I'm on so.
Nick is a horse.
Yeah.
That's right, Sean.
Whereas my sister, should I tell him about Teresa? She's a donkey basically.
You must know.
Because whenever my sister Teresa hiccups, someday I'll have to play this for her, she goes, ah! It'll be very disturbing because it's over and over. She's like, ah! And apparently she can't help herself. So, get the two of you in a room and be like a zoo.
Get Rachel, get Rachel. Just make fun.
There you go. All right.
You
So-
thoroughly embarrassed Teresa. She's not even here.
What's that?
Okay, you thoroughly embarrassed Teresa, but she's not even here.
That's right, yes. She will never know.
We're not making fun of her.
No.
Rachel laughs.
We are
Yeah.
laughing with her.
We are laughing with her.
Really?
What?
said, I don't think she's laughing.
How did she laugh?
I look at Stab and Dusty.
She just laughs in a normal way. She's just
Some people have weird, like they laugh weird.
Yeah, no, she's not one of these like, people,
Yeah.
no. Not
Like
with the
people that
laughing.
snort like every time they laugh.
Yeah, no people
Okay,
snort,
good.
no things like that.
Yeah.
Okay, there's
my God.
kid at home.
Oh, yeah, she does.
Like the leaves, no, there's this kid at home. You get a laugh. It's always really dumb jokes. He says we can steal from his
The heavy breath is still. Sorry, we're discussing different laugh types. Laugh styles. Is that what you're about? Oh my God, I just need to.
You'll love this.
The energy of a continuous charge distribution. Well, if this is the energy of a discrete charge distribution, a bunch of point charges, the natural generalization would be to say, okay, integrate.
What?
Well, in other words, some replaces. No, all right, being smart. Okay, you better. All right.
See what happens second half, once we start moving around.
Yeah.
We get all crazy.
Right.
I get some coffee in
Oh, it is, he's not sleeping anymore.
Oh, no, I'm sleeping.
And next time. I can't say it on tape because it's got, anyway, okay. Natural generalization.
Okay, all right. Got it.
Oh, yeah.
Got
Yeah.
it.
What's the song for?
Shut it!
You're too
Ah.
close to it.
All right. Natural generalization.
No,
Oh, no.
it's okay. We'll discuss after the biggest one.
Would just be integrate rho b tau and multiply by 1/2, right? Because in other words, rho d tau will be the little dq, so sum up all the little dq's times the v's at their locations, and multiply by 1/2, and that'll be the potential energy, potential energy or the work needed to assemble our continuous charge distribution. All right, now here's where we have some fun with vector calculus. Oh yes, it is fun. Oh, big time fun. I am literally getting excited here because I like this kind of stuff, right? That's right, yes.
On the back.
Tingle, tingle, tingle. Okay? We're going to hyperventilate here. We're going to rewrite using Gauss's law. Rho is equal to epsilon naught times the divergence of E, right? Because dV is rho over epsilon naught. So we use the differential form of Gauss's law. Rho is epsilon naught dV. And so that means that we'll get that the work is epsilon naught over 2 times the integral of div E times V d tau. Just replacing that rho with epsilon naught div E. Okay. Now it's time for a vector identity. The following is a vector identity. The divergence of the function fa is equal to f times the divergence of a plus a dotted into the gradient of f. This is directly related to the rule for differentiating a product, a scalar product. In other words, d dx of uv is u dv dx plus v du dx. Generalize that. It's easy to prove this just write out the partial derivatives and the product rule, and boom, drops right out. So that means that we can integrate over a volume of the divergence of fa d tau. That'll be the volume integral of f div a d tau plus the volume integral of a dot grad f d tau. But by the divergence theorem, this first volume integral that we're starting with here, the integral of the divergence is equal to the flux of the vector over any surface enclosing the volume. So the divergence theorem says that this is equal to the integral over a surface which encloses the volume in question of the flux of Fa. So div Fa d tau is the flux of Fa integrated. Or, in other words, the volume integral of f div A is equal to minus the volume integral of A dot grad F plus the surface integral, the flux, of Fa. Just taking the last three and rearranging them. Just, in other words, pulling the A dot grad F over onto the other side. What does this remind you of in single variable calculus when you're doing integrals? It's integration by parts. Yeah, this is a generalization of integration by parts to the multivariable case. All right? So, it's 3D integration by parts. So that means if you just look like a one-dimensional integration by parts thing, if you put on red and blue glasses, it actually looks like this instead. So, applying this to the situation at hand, apply that over here, that says that the work is epsilon naught over 2 times minus the volume integral of E dot the gradient of V, d tau, plus the surface integral, the flux, of VE dot dA. However, there is a simple relationship between E and the gradient of V, that being that
You almost got it. That was good though. We started counting substitutes.
that being that the gradient of V is, no, not a puppy, it's not a puppy. The gradient of V is, what is the gradient of V?
The gradient of V?
Yeah.
Electric field.
What? Yes, the electric field, that's right, yes, thank you. Yes, okay. Minus the electric field.
Sitting here saying that.
Yeah,
He's been like,
I'm just gonna wait till I sit down, that's right. Then that's not gonna satisfy you, so I'm gonna have to lie on the table. And then, all right.
Well, you missed Ben said that.
Ben said it like 70 times.
Yes.
70.
Oh,
So we assumed it was wrong.
But he was-
oh, you said it.
Yeah.
You must shout it boldly.
I thought it was.
No, you must be bold. The gradient of V is minus E. Of course, Dr. Harmon, is what you should have said. And then I wouldn't have missed it.
We all wanted to say it.
Actually-
We just want to take credit for it. We heard that.
Ah.
Then
I
Yasser
see.
clearly being.
I clearly said it is.
I could have said it.
Took it.
Come
on
on.
himself.
Oh my gosh, now you look like Chad. Yasser. Keep going. Keep going, please.
You are messed up.
Oh, good.
Oh, you can't trust that teacher. What are you thinking?
Hold the desk together, you should not remove that. You should not remove that.
Okay, if it's holding the desk together. Yeah. All right.
Still, you can't do that. You go to the office.
Makes you feel any better if you're playlist.
Yeah, I'm pretty sure you
Put it
can.
into a
Private message.
But it didn't really live.
I bet they don't do this in Dr. Teresa's classes.
His jokes are more subtle.
This is way too rowdy. Rowdy.
That's good. You know, Dr. Trees would just whip out his magnum. It's just all right. So we can replace this first integral with E squared d tau. Yes.
Have you seen Sid Magnum?
No, you can't.
Oh yeah.
Rachel, your mouth is great. Danielle's trying to hide a laugh. Like, that's so awkward.
Okay. So that gets a box. Right?
You should write Magnum equation over.
That's right. Yeah.
Where's the days now? Magnum.
Yeah.
I kind of like the writing though.
Over what v shall we integrate? Well, this is this came from integrating 1/2 rho v d tau. So in other words, we have to at least integrate over all the places where rho is not zero. We have to at least integrate over the charge distribution. Where rho is not equal to zero. But on the other hand, there's nothing stopping us from going past that because, you know, if I do the integral 1/2 rho v d tau, well, I have to at least integrate over where all the places where rho is not equal to zero. But if I also include volume where rho is equal to zero, it doesn't make any difference because when rho is zero, you're just adding volume without changing the integral. So there's nothing stopping us from integrating where rho isn't zero as well. So we can integrate where rho isn't zero. In fact, there's nothing stopping us from integrating over all of space. Let's integrate over the universe, shall we?
Yeah.
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 That'd be like a t-shirt, you know? Let's integrate over the universe, shall we? We can integrate over
Let's
all
get-
space.
Well, we're gonna get charge t-shirts this year.
What?
All right.
Charge t-shirt.
Oh, that's for
SPF.
that's right.
Were you
Ronnie,
exclamation
you know, you
point?
integrate over the universe.
Charge.
When did we?
Well, yes, yes, yes.
Oh, I was like,
Yeah.
did we
Like, maybe
decide?
that's, I guess,
I vote for it.
What is the thing?
Q, it's like, when she goes like, running with the light.
I like that a lot, yeah.
Go with it.
And the shields that was really
Yeah.
Yeah, put it in
happy.
the
Did we have the bigger signs? There's electrons too.
What color
You
should
should
it
have,
be?
you catch two of them going towards each other.
Yeah. That would be negative.
That would be a.
No, he said you have
We
some.
would have two negative charges on it, where they, you know, it's positive.
Oh, yeah.
But then they.
A positive is a positive, group on this side, negative.
Yeah.
I think you should just have one charge.
Just going.
Yeah, you said one part, just running.
Maybe on the boards, with like a joust.
Maybe a big proton on that.
Maybe what?
So let's do the volume integral over all space. And then that means that the surface integral will be over the boundary of the universe, question mark. In other words, we're taking a limit here as you just take a bigger and bigger volume and a huger and huger surface that's enclosing all of that volume.
I think you should use the souls.
Hugemer and hugemer.
The souls.
What's that?
Souls.
Ah,
Souls.
that's right.
You know what souls is. You know what souls.
Okay. Now, the thing to note here is that the integral of VE dot dA, if we get really far from these charges, very far away from the charge distribution, eventually the electric field looks like the field of a, what do you think? Point charge, right? Where the total charge of that point charge is equal to the total charge of the charge distribution. So far enough away, effectively, if you get further and further away, you're just seeing Q over 4 pi epsilon naught r squared for the field where Q is the total charge on the system. So in other words, if you get to a really big surface, so the tilde means for a really big surface, this is going to look kind of like the total charge divided by 4 pi epsilon naught r squared times, well, the potential then is going to look like the potential of that point charge, Q total. So it looks like Q total over 4 pi epsilon naught r for the potential piece, so I wrote it backwards compared to what I had here. So I'll just erase this because I can do that. So, because I put the V first, so that's going to look like Q total over 4 pi epsilon naught R, and then Q total over 4 pi epsilon naught R squared R hat dot dA R hat. Or in other words, we're finding the flux of a point charge, if you will. Well, you got the electric field and the big sphere, what am I trying to say? Then times 4 pi R squared, okay, times the area of the sphere. For if the surface gets really, really big, that integral gets closer and closer to being potential of a point charge times the magnitude of the electric field of a point charge times the area of the sphere, which is 4 pi R squared, as R gets really, really big. So that goes to 0 because you've got, basically it's going like 1 over R. So as the surface gets bigger and bigger, that integral looks like 1 over R times whatever the constants are. So that approaches 0 as the surface gets really, really big. Does that make sense? Not make sense? Happiness, joy, lack of happiness, despondency? I shouldn't even ask Corey. Because I know what he might say. And I'll feel all rejected.
Way to go, Corey.
Yeah, thanks a lot. I can't even continue now. Yeah.
Well,
Yeah.
I guess so.
So since the surface integral vanishes if we take the integral over all of space in that limit, then we could say that the potential of our, that the work done to assemble our charge distribution is epsilon naught over 2 times the integral over all space of E squared d tau. Hey, that's pretty cool. Because what that seems to be saying is that we can think of the energy of the system as being stored in its electric field. Because we can just integrate over the electric field to find it. So, interpretation. The energy of the system is stored in its electric field. With an energy density, energy per unit volume, of epsilon naught E squared over 2, because that's what we're integrating over volume to get the total energy. So we'll call that U sub E epsilon naught E squared over 2. Epsilon naught E squared, whatever you want to say. Now, giggling again. Now, we are not forced to make that interpretation. After all, that integral we wrote before is always true. Whether or not I integrate over all space, I can always do the calculation by integrating over any volume that encloses all the charge and then finding the flux of VE through the surface bounding that volume. But it turns out that when you talk about electromagnetic waves and so forth, it really does become natural to associate an energy density epsilon naught E squared over 2 with the electric field. And in fact, for the magnetic field, you can associate an energy density with it of V squared over 2 mu naught, where mu naught is the permittivity, permeability of free space. So that's a wonderful thing to have discovered. Aren't you happy? Yes, I'm happy. And it was done with fun vector identities and stuff. That's just good stuff. All right. What was I going to say next? Oh, so this integral, could this ever be negative? Well, let's see. Can E squared be negative?
No.
not unless E can become a complex number, and not in my universe, okay? So this is a positive quantity integrated over all space. It's a pretty good bet this is going to be always positive. In other words, the energy of a continuous charge distribution is always positive, no matter what. Doesn't matter. Even if I have like, here's some positive charge here, some uniform positive charge distribution, and I say it likes negative charge, so here's lots of negative charge for it to be here. Here, you guys have fun, you know? So there will be negative energy associated with pluses being near minuses and all that, but nevertheless, it's going to take energy to bring all these plus guys together, and energy to bring all these minus guys together. So what this is telling us is that in the end, you always get a positive result. You can't have negative potential energy for any continuous charge distribution. And this leads to the seeming paradox, but wait a minute. Suppose I have 2 point charges. Here's plus Q, minus Q. Is their energy positive or negative? Negative, right? Because we would find the energy to be minus Q squared over 4 pi epsilon naught R, whatever the distance is between them. And the way out of the seeming contradiction is to realize, again, that point charges, if you did this integral for a point charge, what do you think you would get? Well, as you get close to the point charge, what happens to the electric field? It becomes infinity, right? If we do this integral for a point charge, we'll get epsilon naught over 2 times the integral of Q over 4 pi epsilon naught R squared times 4 pi R squared dr. The volume element is spherically symmetric, so you use the volume element of 4 pi R squared dr. So d tau would be 4 pi R squared dr. The electric field is Q over 4 pi epsilon R squared. So in other words, you're doing an integral, ultimately, of constants times dr over r squared, because it's going to be r to the 4th down on the bottom and r squared up here on the top. So dr over r squared, and if you integrate dr over r squared between 0 and infinity, the result blows up. The lower limit causes it to blow up. So the field stored, the energy stored in the field of a point charge is infinite. Oops. This is a continuing source of embarrassment, both to classical electromagnetic theory and quantum electrodynamics. The infinite energy of a point charge that you get by calculating the energy stored in its electric field being infinity. What do we do about it? We say, whatever, and you just ignore it. That's what it comes down to. You just say, oh well. And we say that when we're calculating the energy of this configuration, we're only calculating the energy due to the charges being close to one another, and we just ignore the infinite energies of the 2 individual charges. So we just subtract off the infinity and get what's left over, namely the minus Q squared over 4 pi epsilon naught R. But, you know, when you get to quantum field theory, you discover that subtracting infinity is like, you know, it's something you do every day of the week, you know. So infinity and schminity, just subtract it off and you'll be fine. Quit worrying about it, just enjoy your life, all right? Okay.
You should have said that like in a Freud way.
In a Freud way, that's right. Yeah, Peter Freud, yes. Yes, lovely wife and I both experienced Peter Freud at the University of Chicago. You can see him in various videos. He's a theoretical physicist from Austria. He was fond of saying things like, "You did that in kindergarten." I've told some of you before the story of when he was teaching mechanics, graduate mechanics, and he goes on and on and on about the vector spaces and so forth, all these properties of vector spaces without laying out what they are, just assuming everyone knows them. So he says at some point, oh, I'm very sorry, I've been assuming that everybody knows what a vector space is. Is there anybody who isn't sure what a vector space is? And our friend Mike Leibig neatly raises his hand and says, I'm not really clear on it. He says, oh, it's trivial. It's simply an abelian group with an addition defined. And then he just continues onwards as though that completely answered the question.
I'm not saying at all.
And if you feel good,
An abelian group with an addition defined.
And then beauty.
An abelian group with an addition defined.
Oh, okay.
Yes.
oh.
Yeah.
Oh, that's
Just
nice.
Right.
Yes.
Oh,
Right.
I gotcha.
Yeah, and so he would say things like, if he were teaching us, he would say, so as you would know in kindergarten, for a circularly symmetric charge distribution is simply 4 pi r squared. And then, just and so forth. No need to say words.
Was he being serious?
Somewhat, probably in a way, very smart guy.
Like from kindergarten? maybe?
Well, he's probably exaggerating a little, but, he's a really smart guy.
Well,
And
maybe
he,
he's doing.
maybe he might have known it in kindergarten, probably not though. I think he was probably having a little fun. So, right. So then what was I had to say it like
Let's
that.
watch that.
No, I was saying about the what, the infinity part.
Oh, the infinities, yeah, that's right.
About
Yeah.
infinity.
Yeah. It's trivial, you just subtract off the infinity. Okay.
Someone was spelling. He's spelling his accent. He's spelling his accent.
Conductors in electrostatics. All right then. I'm going to leave it at that.
You do it on purpose?
I did not. Blob of metal. Okay? Because by conductor we mean something that conducts electric currents without resistance. So generally think of it as a blob of metal. So conductor, external point charge. Well, what will happen is that since charge can flow freely in the conductor, then, conductors, they're metals, so you got electrons that are moving in the conduction band of the metal, and there's a crystal lattice of metal nuclei. So the conduction electrons behave as though they belong to the entire metal instead of to individual atoms like the valence electrons do. So electrons are free to flow, and so electrons will build up on the near surface of the conductor. But if the conductor as a whole is electrically neutral, that means that they left some poor little nuclei behind, and so there is positive charge on the other side of the conductor. And if I drew it carefully, I'd have as many negative charges as positive charges overall to show that it's electrically neutral. So let me get rid of some of those negative charges that I carried there. So something like that, whatever. So Q draws negative charge towards it, and that leaves positive charge over on the other side here. Yes, okay, I couldn't tell. You're hiding your mouth, so I thought you might be giving me.
No, that's this kid. He's just jovial today.
Ah, I see.
That's joke.
Induced charge.
Oh, he said that was funny.
Think of pause for other reason.
Conductors have a whole list of properties that we'll discuss one by one. Electrostatics, again, means we are looking for equilibrium configurations. One property, kind of surprising, E is 0 everywhere inside of a conductor. No two ways about it. E is 0 everywhere inside of any conductor. Is that Nope. Okay.
I mean, if he's zero, then he's
Well,
zero.
yes, it is negative E is equal to 0.
Is that something dot E?
Oh.
Yes, that's right. I'm actually talking about the one form.
The one.
That's right, the one form associated with E, which is waiting to pair up with a vector and thereby produce a scalar. Yes. So E is 0 everywhere inside of a conductor. And actually what I just said made sense, by the way, about the one form. We're not going to go into it, but that was meaningful, believe it or
Oh,
not.
you're so smart.
Anyway, E is 0. I didn't hear that. Could you help me
She's
with
not
that?
gonna repeat it again?
You're so smart.
Offer it.
No. I am trying to whet your appetite for future adventures in mathematics. And yes, I am smart. I am so smart.
I'm writing that down.
Yes. Yeah.
I'm sure like that. I am smart.
Yes, Dr. Right. A, dumb, B, smart, and C, so smart.
Obvious answer is.
Why? Well, if you assume that you can actually do electrostatics with conductors, if E wasn't 0 in here, hey look, electric field, I'm an electron, I'm going to flow in response to that electric field. Charge would flow. That's what it does in a conductor. If there's an electric field, charge would flow. Because the conductor has very low resistance. Ideal conductor would have no resistance, so charge would flow. So, in other words, by the time you've reached static equilibrium, the electric field has to be 0 inside the conductor. Now, right when you bring the charge up, it's for a very short time, very tiny fraction of a second, there's a non-zero electric field in the conductor, and then the charges say, wee! In response to that electric field, that's what brings them over to the surface near the charge, or repels them to the other side, or whatever. So for a brief moment, the briefest of moments, there's a non-zero electric field, but by the time the charges are done redistributing themselves, it has to be true that there's no more electric field in there, because otherwise they would keep redistributing themselves until they've reached the situation where the electric field has become 0. So therefore the electric field is 0 inside the conductor if we are, in fact, in an electrostatic situation. From this it follows that the charge density, the volume charge density, is equal to 0 everywhere in a conductor, which follows trivially from Gauss's law rho is epsilon not div E. So if E is 0, div E is 0, so rho is 0. But and the next property will be discussed next time.